Yeah, so yesterday we had a look at functors and we gave some examples. So that's the definition. We actually defined that using a similar naming convention as the one we use for monoid homomorphisms because the idea is basically the same. It's a structure preserving transformation from this time one category into another rather than a monoid into another. And so we saw that this time around we needed to have two underlying functions, one that's mapping objects to objects. Okay. So if we're thinking of categories as graphs with some structure on the some constraints on the edges that we have, this transformation is telling us how we are mapping the nodes of the graph S to the nodes of the graph in T. It might be a subset of these, right? We don't necessarily need to cover everything. But then we also need to map all of the edges to corresponding edges. And then we have extra properties, just like we have for monoid homomorphisms, saying that the um, operations that we have in the S category and their equivalent operation in the T category are behaving well with respect to these transformations. So identity is taken to identity and composition is taken to composition. Um, and then we gave some examples. So we have the identity functor, which is not changing anything. And we have the and then functor, which given functor from S to M and another one from M to T will give you one from S to T by just applying both sequentially. And then we saw an interesting one, which is a bit like Crush for monoids, but this time it's for categories now. So it's taking an arbitrary path where the relation telling us whether we can take a step from a point to another is given by the set of morphisms in the category of interests. And then we can just crush this whole path into a single C. And because we know that um, composition in C is associative, then we know that this path is respecting like all of the constraints. Well, this operation is respecting the appropriate constraints. Then what did we see? We saw map.
Yeah.
So
So this is doing something quite structure enhancing because what we're saying is that we've got two relations, RA and RB, and we don't know whether or not they are themselves the morphisms of a category. We don't know whether this graph is reflexive or transitive. But if we say, okay, let's take the path closure of that thing, then we know we definitely get a category. And if we know how to turn RA edges into RB edges, then our function that turns edges into edges becomes a functor that turns paths into paths in a way that respects identity and composition. So that's cool that we actually we get some laws coming out of nowhere because pathness enforces categoricity by brute force. And we were on our way to a nice little gadget here where what's going on? Uh, you say that you have some functor that comes from a path category, and I'm going to tell you how you did it. In particular, I know that I can turn a single R edge, and remember, R is not necessarily a category.
yeah.
But I know how to get a morphism out of it because I can pack it up as a singleton path and feed it to your functor, and that will get me a morphism in our category, which we're currently calling T. Right, so that's enough to get me somewhere. And let's figure out how. So we're going to construct another functor. I don't know, fun prime,
Yeah, should I call this now?
fun gun. Yes, yes, yes. Is a path R to T.
Ooh.
Right, and it's going to be map something and then something.
Well,
Yes, map, edge map, and then
maybe
you
not.
might need some parens. I don't know.
I think I need some extra argument. Ooh, that's
Let's-
weird that it parsed.
Um,
Cannot refine. Oh,
Uh,
it's taking two functions.
yes.
Where's map?
What's it? Has it got some?
It's only
Yeah, it
taking
looks like it should take two functions and give us a functor. So,
Oh, I know.
right. Ha ha ha. Classic. It's not actually infix at all. Hilarious. See, let that be a lesson.
I'm just
Don't
dying.
write infix operators that consist solely of letters because you'll easily mistake them. You'll get confused about whether they're infix or not.
All right, so this should be my edge map, and then
That should be the identity, I think.
wait, is it not F option?
Oh, okay, it probably is.
Yeah, but I don't know why it's not solved
Um,
by unification. Oh, it's a bit too
we'll figure this out in a
Okay.
moment, but then this is going to be crush.
crush. Okay,
Um,
over T.
right. Okay, so now we've got a functor that says what we do is for each of the R edges that come in, I'm going to turn that into an honest to God morphism by using your functor on singletons. And then when I've got all of those morphisms, I'm going to crush them together to make one big thing. And that's going to do exactly the same job as your functor. Because the point is that if your functor obeys the functor laws, you ain't got no choice but to agree with my functor. So, yes.
So we want to prove
We would
this.
love to prove that. I think we should probably not. We should do the essence of it, which is to prove that they agree on morphisms.
Okay. So fun. Category.
So we're going to prove that if we've got S and T in, yeah, let's just prove the equation actually on the. So this.
Oh no, it's a functor.
Yeah. So let's actually.
Yeah. So it's.
Let's prove.
So it's home fun. Is this what you want to prove?
More or less, but it's not. It's not the right thing. That's.
Do you want to type it maybe?
Yeah, I was hoping just to prove something more directly. Let's see if I can say for all S and T.
Oh, I see. Okay.
If I've got a path R S T, something like that. Okay, so far, up, my fingers. Right. Then what I want to say is that hom fun, is that what it's called? It's f dot hom fun. Yes?
No, it's fun. Fun.
Well, we've got
it's called
yes,
it F. Okay,
up there, yeah. So that's I need this is R's of that type. Need to name it if I'm going to prove stuff about it. So F hom fun R's is equal to something. This is taking a while. Or is it just that it's a little bit confused?
Everybody's busy. Oh.
That's a little unfortunate because I would quite like to be busy instead.
Yeah, just kill it.
What's that? Right, that's more like it.
Mm-hmm.
And now I need to say that this is equal to, this is going to be annoying. Oh, maybe I'll let's just say module f prime
Oh yeah.
is f dot hom. Oh, sorry, is
No, yeah.
fun prime, yeah? Are we happy?
Mm-hmm.
Reasonably so. All right, and then this is going to be f prime dot hom fun r's. Okay, and now I'll. Oop, my fingers do crazy things.
Control C, Control F will jump
Yes.
to the nearest one.
Okay. So let's see how we go. This is the guts of it, is that these two things are going to do the same thing to any given path. And
Yeah, so crucially, we don't know anything about the F home fun, only that it exists. But the one on the right, we know that it's a map followed by a crush.
yes.
So
So funnily enough, if I do that, I need to know that whatever f hom fun does, I get back the t identity. You know, when I feed it the empty path, I get the identity. And I think if we're fortunate, what was that called?
identity dash identity.
I'm not sure it's true.
Mm-hmm.
It's called, oh, yes, it is identity. Fine. Should have had more faith. F dot identity. Looks good to me.
Mm-hmm.
Now,
Right.
here we've got an R, and I suspect we will need to do a bit of jiggery pokery here. But let's see what we've got.
Is it not just?
I have to make it do some normalization.
Uh-huh.
Right, and then this gets to be a little bit exciting, but let's not panic. Can you? This is going to involve equational reasoning.
Or rewriting.
Okay, maybe I could try rewriting, but let's see what happens. So we've got, is it called f dot and then?
And then, yeah.
And then, how camel is my case?
Yeah.
Good. Okay. So this is going to be r cons nil. It's going to be one of the things I want.
Mm-hmm.
So you can see that's useful. And I'm also going to want oof. What was that anyway?
It's ours, right? That second path.
Well, no, it's not, is it? Or maybe it is.
Yeah. Because and then is append basically, right? And you're saying R cons R's is the same as singleton R appends R's.
Right. Right. Okay. So what I've got is good on the left-hand side. So let's see if I can pick it up. and that's Control W, rewrite Control Y.
Mm-hmm.
Right, so that's some progress. And now I think I want to say also I want to rewrite by wow R's. And let's see if we're lucky. Well, that looks pretty good to me.
Mm.
So no, you didn't have a choice. All you could do, what we're saying is the only way you can make, the only choice you have when you're making a functor is to say where you send each individual edge. And apart from that, you've got no freedom whatsoever. The fact that the laws have to hold means that any path you made up of those edges has to turn into the composition of the morphisms that you chose for each individual edge. There's no other way to make a functor out of this path object. So that uniqueness of the way to do it is really very helpful. It tells you that you not only know how to make these functors, you know that they are characterized in a very particular way, that your only freedom is where to send each individual edge.
Machine is not smart enough to know that.
I don't need you to tell me how stupid this machine is.
Possibly
have the pain in the ass situation where you wanted, say, to find a natural transformation, or you wanted to find an equality through natural transformation, and the code makers are, or like have to be the same because of how functors work. But unfortunately, you need to prove that the laws are the same yourself. It's a miserable time.
Yes. The message is, of course, that we're still living in a world where all Agda gives us for free is to obey the definitions that we've written computationally when you feed kind of things with constructors in.
Yes.
The moment you feed in things with variables in, that gums up the works, and Agda says, I'm sorry, I don't do algebra, I only do arithmetic. So, and we're in a situation where we're trying to fit things together, where just a little bit more algebra would save us a lot of pain. And yeah, it's not there yet. But we can get somewhere. Are we going to manage this?
Well,
How much of it?
we'll get some of the way.
Yes.
We'll see whether we can get all the way.
Um,
But the idea, so as Connor was saying, here you don't have any choices, right? And often you don't have any choices. So because and then is associative, we know that the way in which you're bracketing your expression doesn't matter, except that for Agda it does matter. So you end up having to prove these equations between things that are bracketed differently. And so then the idea is that can we do better? And it turns out, yeah, you can write a little program that will check whether two equations, whether two expressions are actually equal up to these laws.
Yeah. So
and
let's just figure out what the game is. We know about categories, and we know that they absorb identities and are associative. And we know about functors, and that they preserve identities and respect composition. So that's a collection of 3 laws per category, 2 laws per functor, which allow us to build up expressions which involve identity and composition and map. And we have all sorts of ways we can rearrange those expressions without changing what they mean.
Yeah.
And we want to make sure that we've got some way to standardize the representation of these things so that we can actually get Agda to compute a bit of algebra for us. And that would be nice.
So I won't quite do functors yet, but we'll see if we can get through this already. So let's see an expression. So we are going to be talking about our morphisms, right? So our expression, it's going to be just like for paths. they're gonna have a start point and an end point. So they're gonna be CO to CO. I suppose I can make the source a parameter. No, I cannot.
No, you can't.
Okay.
Well, maybe, yeah. No, you maybe can, actually. I mean,
Oh, there. Yeah, but then it's a non-regular parameter. Yeah.
well,
anyways.
I mean, okay, so for sure, it's, sorry, speaking in code, for sure, it's a Protestant index, not a parameter.
Right.
But, uh,
But let's just say, okay, I'm gonna throw in syntax of expressions, just like we had expressions for a small programming language. Now we want a syntax for our compound expressions of like morphisms and compositions and stuff. And so we're gonna write them like this. We're gonna give ourselves some kind of.
have we got, so it's, that set needs to
Oh,
be.
yeah. So here I'm storing an element of the object, so it needs to be at least C.
And it's going to need
And
to
then
be
I
at least L.
anticipate that.
Yes, any
I'm
minute
gonna,
now. And,
yeah, that's unfortunate, but
right.
so. All right. Then I can have just a morphism. Should I write it like this or something? I don't know.
Up to you. I like Square for that job, but
St-
actually, sometimes I'm terrible and I just like backtick for that job.
Oh, like this?
Yeah.
Sure. So if we have an arbitrary morphism in C, we can just turn it into an expression with the same source and targets. So we're just saying, okay, this one, I don't know how it was built. It's just abstract. It's sitting there. But we can also have a syntactic and then. And the benefit of this is that we're able to see that the expression is built using and then.
Right. Yes.
So it's an SMT.
So crucially,
Express.
expr is not
MT.
a category because this here and then is a constructor, and
Oh,
you
yeah.
can look at these things and tell that this thing is a left nested and then, and that thing is a right nested and then, and you see what they say, not what they mean, and they say different things. But we're going to show how to tell when things which say differently mean the same.
Yeah, if I try to write this, and then G, and then
Yeah, you've got too many backticks.
H equals.
left.
Oh, although that was not bad notation.
It's-
And then G, and then
Yeah,
H.
this is in fact manifestly false.
Well, yeah, I should even be able to prove this, right?
Yes.
If I open import data empty base using bottom.
Oh.
Do we not have a base one? Okay.
I don't know. Right.
Right, so they are different syntactic objects. They are parenthesized differently and therefore they're different.
This, by the way, involves a slightly more sophisticated bit of unification that we're used to, but only very slightly. Because what's happening is that if you compare these two things, you've got to match up the and thens, if you would oblige, by inserting some spaces
Where?
here,
Oh.
just to line up with that thing.
With what thing?
No. The outer and thens in both cases should line up. So this and then wants to go there. So
What?
yeah, space it out so that the outermost and thens are vertically aligned.
Oh, I see. All right.
Right. So okay, for this equation to be true, we need f to be equal to something that's got an f strictly inside it.
Mm.
And here we need h to be equal to something which is strictly bigger and has an h inside it. So we're basically saying, you know, we need n to be n plus 1. You know, it's, you know, that we've got an inductive data structure where something is inside itself. Right. And Agda's smart enough at unification to realize that's impossible.
Mhm. Okay. So these things are actually standing for proper morphisms from the source to the target, and we can give a semantics that will take an expression from st. I want to say variable sm to t co. Just leave me alone. I don't want to talk about these things explicitly. So it's taking such an expression and it's going to return a proper morphism from S to T. And how do we define that? Well, we look at the syntax and we turn the syntactic constructs into their semantic equivalents. So the syntactic identity becomes an identity in the category. Here we add a morphism sitting in there in that
It's just wrapped up, so we
backtick.
just unwrap it.
So we just put it like this. And then these ones, well, we take the meaning of E1 and then C and then the meaning of E2. And write it like this.
That's a little evaluator.
All right.
Yeah.
Do I want to do this one? Yeah, sure. So just like we did for our correctness of optimizations of a small language, we can define what it means for two expressions to be semantically equal. So we're going to say if I have E1, E2 expressions between S and T, then I'm building a set
Of set underscore.
L.
So
E1 is semantically equivalent to E2
is it not
whenever.
going to be C label?
Well, it's a propositional equality, right?
You never know your luck. Yeah. Okay. Right.
Okay, now.
So yes, we're in the gate. So that's to say, if you see a categorical expression involving identities and then and other stuff in the wild, you can turn it into one of these expressions by turning all the identities into backtick identity, all the and thens into backtick and then. So you take the actual things and replace them by the syntax, and then anything which is indigestible, you turn it into, you just wrap it up with just backtick. And that gives you an expression whose meaning is the expression that's in front of your nose. Right, so that's, you can undo, you can read, if you can read, you know how to undo this Scott bracket interpretation to give yourself an expression. So if you're trying to prove an equation with like different grouped compositions and stuff on both sides, you can quote both sides of it to get the expression that corresponds to the left-hand side and the expression that corresponds to the right-hand side. And then the thing you're trying to prove is exactly that these expressions are equivalent.
So they're not equal on the nose as syntactic expressions, but they're semantically equivalent because their interpretations can be proven to be equal up to some proof steps. The whole point is that we don't want to be doing these proof steps. We want to say, this is syntax. So you should be able to like inspect the syntax and realize that you have F, G, G, H, H. The brackets don't matter. Don't bother me about like actually proving that these are equivalent. So how do we do that? Well, the idea is to find a different set of values. It's to find a set of values that we can target and in which equal expressions will be equal, will give rise to equal values on the nose.
Yes.
Exactly. So we want to transform our syntactic expressions into different expressions while preserving the semantic meaning, so that if the things are semantically equal, they are mapped to the same elements.
Yeah. So that the idea is that we're going to do kind of stuff like we might have kind of our expressions might be made from compositions. They might have the odd identity dotted about in silly places, but there will be, at the leaves of these things be some packed up morphisms, and we need to pick up a standard way to rearrange this tree. And I've got a funny feeling that we're going to pick this one. Kind of nil. We're going to make a path. We've got a notion of path already that just says, can we figure out how to join these things up in a sequence? So we're basically just kind of reassociating to the right all over the place, shoving a nil in at the end, even if we don't need one. And so let's see.
Yeah, because morally this is saying like I'm going to put these two sub-expressions and then parens around them. But if you turn it into a path, because you've linearized everything, you've gotten rid of all of these annoying parens. So let's do it. We have our expression. We're going to match on it. If we have the identity, well, we could do something silly like saying we have the identity and then something like this. But then we've introduced garbage in the representation, right? Because we have these unnecessary steps that are getting in the way. And it should actually be the case that something composed with the identity is the same as itself. Like you don't want to be keeping these needless identities around.
Bad choice.
So that's a bad idea. But instead we can just pick the base case, which itself is interpreted, if you remember, as the identity when we crush a path into a single morphism. If we have a function sitting there, well, even Agda can find what the answer is. We're doing this. And then if we have two expressions, my naming scheme is horrible. What do we do? Well, we're going to linearize the first expression. We're going to linearize the second one. And then how do we build something linear out of two paths? Well, we just put them side by side using the transitivity proof. So eval E1, eval E2. Right? So now we've simplified these arbitrarily nested expressions into just a path of values where we've removed all the identities, but that's only possible because these were presented by syntactic objects, right? We don't know whether we would be able to detect a wild identity sitting there. So we're really relying on the fact that this representation has done that isolation of these identities for us. Okay, so we've defined evaluation. Should I prove it correct first?
So that's
or
normalization rather than evaluation.
well, I don't know, normalization.
Or do you want to say,
I would want to say this.
to
C and
Okay,
ST.
fine.
Norm, normalize. E is, what do we do? Well, we crush the evaluation of E. And that doesn't check because
you need to say C. Crush takes it an
C.
explicit category.
Yes. Right. So eval, we associate everything to the right because it's building a list basically. And then we crush the result into a single one. And crush of, so two trees that are nested differently but have the same leaves. When you build the list, you're building essentially the list of leaves that are not the identity. So you're getting them in order. And then crushing is doing always the same kind of nesting. So you can see that if you were parenthesized a different way here, you'd still end up with GH. And the crush would again give you the same value.
Yeah, we're saying that all that's important
Yes.
is this sequence. It doesn't matter what the bushy structure of the tree above the sequence is, just the sequence is going to tell you everything you need to know. So that's what we're actually doing. Our eval here is finding the sequence. It's just digging it out from the tree.
Let's see, maybe I can prove normalization correct directly?
Right. Well, the good move is always to say that if you interpret E, yes, that's the thing to prove. So that's to say, if you evaluate this, if you interpret this thing directly, or if you squish it all into one path and then crush it, same answer. And this is going to work.
Right, but this is where we need to do some work, right? Because this interpretation here will turn ID into, well, where is it? The proper identity, and then with that exact split, there's the crush will reassociate everything.
Yeah.
So that's where we need to do some work.
Well, we knew we were going to have to use some category laws somewhere. And this is where.
But we do it once and for all. That's the whole point, because it's talking about any expression whatsoever. So we will be able to apply it all over. Okay. Well, this is just true, because one of them got mapped to the identity directly, and the other one got mapped to the empty path, which itself becomes the identity when you crush it. So that's true. If I have just F sitting there,
then you will find that you need a law.
yeah. So on the left-hand side, we normalize F to the singleton path. And when we crush the singleton path, okay, we could have been more clever when we define crush, so that we skip the last element, but whatever.
It's not worth it, you know.
We have to pay somewhere anyway. So.
Yeah.
Okay, so this is C.
And then identity, I think it's called.
Okay. And then this one, okay, let's do it nicely. Being up, 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 and then, all right.
Yes, you might. Okay.
So I have a crush of a transitive of two things. If you remember, crush distributes of a transitive, because I mean crush was defining a functor, right? So we had this result here.
Oh, you don't want to do that.
It will be shaped like this, but there's a simpler expression than that. Okay, it's not quite. And then eval E2. All right, so normalize of E1 and then E2 is crush of the transitive of eval E1, which itself reduces to crush C and then crush C. That's good. And this is actually just well, maybe I can leave it. Can refold it on the way out as a just an equality step for clarity, right? This is just normalize E1 and then normalize E2. And what I want to prove here is, okay. Is that this is equivalent to E1 and then E2.
But,
and this is really exciting because I have, and then in the middle, and then I have stuff about E1 and stuff about E2, and both of them are just the induction hypothesis. Normalize E2, correct, E2. Okay. So now, do I want to define this?
No.
Or who cares?
You've done.
Oh, it is kind of cute, I think, but later on. Oh, but I don't have enough.
Yeah, don't bother.
Okay.
Get to the punchline.
Right, so magic. Yes.
um,
Okay. So magic is telling me that if I have two expressions, E1 and E2, from source to target, maybe I should put these. No, that's
no,
ambitious.
you do.
That's
You
never.
always need
Yeah,
to
yeah, yeah.
give the quotations explicitly.
And the normalized version of these two are equal, then these two are equal.
Yes.
And how do I prove this? Well,
Well, okay. There's it's a bit more direct. There's a direct way to do it.
is there?
Oh, not quite. No, I guess you do need to do this.
So I know that any E is equal to the normalized version of it. So from E1, I can go via normalized corrects for V1. Okay, I'll need more steps, so otherwise
Yeah.
it's going to complain. Whoop, 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 whoop. Maybe another one too. And then that should be enough.
Yeah.
So because normalization is correct, I can go from the meaning of E1 to the normalized version of E1, which I know is equal to
No,
the
hang on.
normalized of
You
E2.
don't want normalize E1 equals normalize E2. You want eval E1 equals eval E2 in the statement.
Right, yeah, I mean, that works too, yeah.
It's,
okay. Crush C of eval E1, which is by congruence with the equality that we have equal to this, which is exactly normalize E2, which by normalize corrects is equal to E2 itself. So we've reduced the problem of proving that two expressions, which are potentially arbitrarily nested, are equal, to proving the fact that the paths that we derived from them are equal. But because the paths are, like the path representation is unique, because it's removing all of the identities and the arbitrary parens, etc., it should work everywhere. So
yes.
let's see. If I grab my old example.
We should, yeah.
Took. Yes. So this should be magic of whoop.
Yeah, need it. Yeah.
And then I need to prove this thing.
But what is it?
What?
Yeah, so if you normalize that goal.
Oh, no, I screwed myself here. Ha ha ha. Because it these are arbitrary expressions in the
Yes.
original example.
Yeah, you need
but
there. Yes, you need to backtick everything. You need to just make just remove the underscore. Make backtick an ordinary function, and then it'll be fine.
Oh, okay. If I can find it
somewhere up there, yeah, just do that. And
oh, but it's gonna screw everything. Oh.
Yeah, and you'll need the same thing in the actual.
Okay.
Yeah. now something fun will happen.
Right.
Yeah, same list in both sides. Job done.
Right, but that's not super satisfactory because it feels like we cheated. But instead, couldn't we do, even if we have arbitrary expressions, we know how
no,
we have their meaning, right?
no.
Yeah, I think that should work. Because we're saying that we are not
Oh,
inspecting
yeah, you can do that. You
the
can do that.
content of it, right? Because otherwise, I mean, it feels like we did call it magic, so it's fair if we're cheating. But it is real magic.
Yes.
There's no need to cheat, right?
Yes.
We could take our original expressions because that backtick here is basically a black box that allows us to just package anything we want. And in particular, if we have, even if we're proving something about arbitrary expressions, we can say, well, I don't really consider these sub-expressions to be full-blown expressions. I just want to shove their meaning in that like leaf here. I don't want the full subtree, I just want its meaning here.
Right. So what the backtick enables you to do is to exactly draw my red wavy line that says this is the part of the tree that the syntax is talking about.
Yes.
And the rest of the stuff is what it is.
Right.
Right. And we've got 2 minutes of science left.
Right,
And that's
so
no bad. Yeah.
Yeah, this is even true, right? The goal doesn't need to be talking about exactly where we're stopping the
Yes.
evaluation. It's purely in our, okay, so now
Yes.
we're really not cheating.
Yes.
We really have the same goal that we had originally. It's just that in the quoting process, we're making the distinction between what we identify to be syntax versus what is purely semantical in nature.
Right.
Okay, I'm happy with this.
Yes, that's good. Right. So you can play essentially the same game if you want to throw in functors and functor laws as
Yes.
well, where what you do, the appropriate notion of normal form is a path where each element in the path is some bunch of map operations wrapped around a single morphism that got backticked. So that's to say, anytime you see map of a composition, you turn it into a composition of maps. Anytime you see map of the identity, you throw it away. Anytime you see map of a singleton operation, they just pile up.
Mm-hmm.
And then you can play exactly the same game. It's always the deal. You've got your direct evaluator that follows the structure of the syntax. You've got your thing which generates a normal form, and you know how to interpret that. And you say, I'm going to prove that the direct interpretation coincides with going via the normal form. And when you've got that, then exactly the structure of the proof that Guillaume did a moment ago, this thing here where the step in the middle of Kong, right? Yes.
Which one?
So it's always, the statement is always, the normal forms coincide syntactically, so the meanings coincide syntactically. And the proof always ends up with a step in the middle where, so here we happen to have crush C lying around, but this is how you get a meaning from a normal form.
Mm.
And this is always like, well, you know, as the normal forms coincide on the nose, then they must have the same meaning. And as the normal forms preserve the meaning of the original expression, then the original expressions must have had the same meaning as, you know, as the trick. And it's a very useful trick, which we do all the time to all sorts of little sub-languages of algebraic problems to make them go away.
Yep.
Well, that looks like a good note to end on.